In this video, we're going to talk about the nature of the first and second differences for quadratic functions. So you may recall from grade 10 that quadratic functions have second differences that are constant and not zero. To illustrate that, let's consider the first two examples here. We have example of a linear function, 2x plus 1, and a quadratic function, 2x squared minus 3x plus 1, and we have a table of values. So for the linear one, you'll remember the first difference is like how much you add every time. In this case, to go from -3 to -1, you're adding 2. To go from -1 to 1, you're adding 2, and so on and so on. And you'll notice that the first differences are constant for a linear function. Okay. Now, if you do your second differences, which are like the first differences of the first differences, to go from 2 to 2, you add 0. And that's true all the way through. So the second differences are also constant. They don't change, but they're always 0. So that's for a linear function. For a quadratic function, you'll see it's somewhat different. So the first difference is, again, you're going to think about what number you need to add to get to the next number. To get from 15 to 6, you need to subtract 9. So that's your first difference. To go from 6 to 1, you need to subtract 5. And so on and so on. So you get -1 plus 3 plus 7. So you'll see that the first differences are not constant, but they are linear, right? If you look at the second differences, these actually go up by 4 every single time in this case. So not only can we say it's not constant, we can say the first differences are linear, and the second differences are constant and also not 0. So that's how you tell the difference between a linear and quadratic function based on the table of values using so-called finite differences. So let's take a look at these 3 examples with the table of values down here, ABC. The first one, you have 0, 5, 1, 6, 2, 7, 3, 8, and 4, 9. And we're going to look at the first differences. You'll notice every time you add the same thing, which is 1, so it's linear. If you did happen to do the second differences, you would be adding 0 every time. And that also fits with it being linear, right? If it's quadratic, then it shouldn't be 0. Part B, you have 0, 3, 1, 4, 2, 7, 3, 12, 4, 19. And again, let's try the first differences. So to get to 3 from 3 to 4, you're going to add 1. 4 to 7, you're going to add 3. And so on and so on. So you'll notice that the first differences are not the same. So it's not linear. But if you look at the second differences, you'll notice that you add 2 every time. And that's always the same. Based on this second difference being constant but not 0, we're going to say this is quadratic. You'll also notice that the first differences go up by the same amount every time, so it's linear. That also fits. The last one, you have 0, 0, 1, 1, 2, 8, 3, 27, 4, 64. You may recognize this function, but if you don't, let's calculate the first differences. It's going to be 1, 7, what is that? 27 minus 8 is 19. And then 64 minus 27 is 37. So, okay, it's definitely not linear. It keeps changing. Let's try the second differences. So to go from 1 to 7, that's you add 6. And then 7 to 19, you add 12. 19 to 37, you add 18. Second differences are not constant either. So it's not linear and also not quadratic. In fact, this is cubic. Okay. You might recognize that this is x cubed in this particular scenario. And if you were to look at the third differences, those actually are constant. Well, if you continue the pattern, you would notice that they're constant. And that's actually characteristic of cubic functions.